The last thing we're going to do is learn how to find percentiles using normally distributed variables and work some examples. To do this, we're going to have to work the process backwards. So, for example, working it backwards, suppose we wanted to find a point Z on the standard normal calculator that would produce an area above Z of 0.02. To do this, we're going to use the normal calculator on StatCrunch. And this is how it works. We'd pull up the normal calculator, would make sure it was set to standard. We would have the mean of 0 and the standard deviation of 1. And greater than means we want the top 2%, not the bottom 2%. And we would set the area equal to 0.02. And the calculator reports back a z-score of 2.0537. Let's do one more example before we move on to a concrete problem. Suppose we want to find the value of z such that the area under the standard normal curve in the left-hand tail is 0.05. We would have it set to standard, mean and standard deviation of 0 and 1. The lower tail, so less than or equal to, and the lower tail area, 0.05. The z-score is negative 1.645-ish. So here's the secret. To do a concrete application, we want to work the formula that we're familiar with to find a z-score. We want to work it backwards. We want to solve it for x. So to do that, we're going to multiply both sides of the equation by sigma. Then we're going to add the mu, or mean, to both sides. And kind of switching the left and right-hand sides, we come up with this important rewrite of the z-score. The value x in question is the population mean plus the z-score that created that area times the standard deviation. So here's one of a couple of concrete examples. We know that the lifetime of a calculator has a normal distribution with a mean of 54 months and a standard deviation of 8 months. What should we have as a warranty period to replace a malfunctioning calculator if we don't want to replace more than 1% of the calculators sold? So that is subtly asking us, what is the z-score for the bottom 1%, the worst 1% of the calculators? So first we're going to find the z-score for the bottom 1% by putting a less than and plugging in 0.01 for the area. We're going to use the formula to solve for x, 54 for an average, negative 2.33 is the calculator reported z-score, and 8 is the standard deviation. So we do the math and we find we should warranty it for 35.36 months. So the warranty period, if we were to round that down a bit to make it 35 months, if we warranty it for 35 months, we shouldn't have to replace more than 1% of the calculators. Another example. Almost all high school students who want to go to college have to take the SAT. In 2002, the mean SAT score, both verbal and mathematics combined, was 1,020. Debbie's going to take the test soon. We're going to assume that she takes the test and that the mean of the test is 1020 with a standard deviation of 153. What does Debbie have to score so that only 10% of the people taking the test will score higher than she does? So we appeal to the standard normal calculator. We're looking for the top 10% of the z-scores, greater than or equal to for the top. 10% is the area. We get a z-score of 1.28. We use the formula to find the SAT score, namely the x value. We put in the mean SAT of 1020, the z-score that cuts off the top 10%, 1.28, and the standard deviation of 153. We do the math, and that cooks up to an SAT score of about 1,216. So if Debbie scores 1,216 on the SAT, only about 10% of those people taking the exam will do better than she does.